There is no dark matter to see in the night sky. No faint glow marks its position. No telescope can gather its light because, as far as astronomers can tell, dark matter does not shine, reflect, or absorb light in the ordinary way. If you look toward a galaxy rich in it, your eyes would still be drawn to stars, dust, glowing gas, and the pale structures that visible matter makes. And yet the galaxy would be telling you about something else. You would find it in motion. A star far from the bright center of a spiral galaxy moves under the pull of gravity. The gas around it moves as well. From those motions, astronomers can estimate how much mass must be present to produce the gravity they measure. Again and again, the answer is larger than the amount of matter that telescopes can see. The missing part does not announce itself with light. It leaves a gravitational trace. That is the path we will follow tonight. Not toward a single object and not toward one dramatic discovery, but through a sequence of measurements spread across the universe. The motions of stars inside galaxies. The motions of galaxies inside clusters. The bending of light around concentrations of mass. The faint imprint of structure carried in radiation from the early cosmos. Different observations made with different instruments on different scales, all pointing toward a similar conclusion. There is more gravitating matter than the luminous universe appears to contain. Astronomers call that unseen component dark matter. The name can sound more certain than the science really is. It does not tell us what the substance is made of. It describes a problem. Something behaves as mass. Something contributes gravity. Something helps shape the structures in which ordinary matter gathers. But the particles, fields, or deeper physics behind that behavior have not yet been identified. In the standard cosmological picture, dark matter outweighs ordinary matter by roughly 5-1. That means most of the matter associated with galaxies, clusters, and the growing cosmic web is not the familiar material of atoms. The stars that fill astronomy images, the planets around them, the gas between the stars, and every physical object you have ever touched belong to the smaller share. This does not make the visible universe unimportant. It makes it easier to understand why light alone cannot give us the full map. Gravity can. Gravity responds to mass, whether that mass shines or not. It changes orbits. It holds systems together. It curves the path of passing light. Across enough observations, those effects become a kind of indirect image. Not a photograph of dark matter itself, but a record of where its influence appears to be. So the journey begins with a useful shift in attention. Instead of asking what the universe looks like, we can ask how it moves. Instead of searching for a hidden object with a particular shape, we can follow the places where gravity seems stronger than visible matter can explain. The first clues were not found at the edge of the observable cosmos. They emerged much closer to the familiar scale of galaxies, where stars move in patterns that can be measured night after night. And once those motions were taken seriously, the bright parts of a galaxy began to look less like the whole structure and more like a small illuminated region inside something much larger. The light shows us where to look. The gravity tells us how much is there. The first strong clues did not come from the graceful rotation of a single spiral galaxy. They came from a crowded region of space where hundreds of galaxies moved together. In the early 1930s, astronomer Fritz Zwicky was studying Coma Cluster, a large gathering of galaxies hundreds of millions of light years away. By measuring how rapidly some of those galaxies moved relative to one another, he could ask a simple gravitational question. Was the visible mass of the cluster enough to keep those galaxies bound together His answer suggested that it was not. The galaxies appeared to be moving too quickly. If the cluster contained only the material that could be accounted for from its visible galaxies, then gravity should not have been strong enough to hold the system together in the way astronomers observed. Zwicky concluded that a large amount of unseen mass might also be present. It was an unusual result, but not yet the beginning of a scientific revolution. Astronomy in that era was still learning how to measure galaxies reliably. Distances were uncertain. The masses of stars were uncertain. The relationship between the light of a galaxy and its true mass was not yet well understood. There were many reasons to wonder whether the discrepancy would survive better measurements. So the idea remained, not accepted as a final answer, not forgotten either. For several decades, the problem of unseen mass existed in the background while astronomy improved its instruments and its understanding of galaxies. Then the measurements moved inward. Instead of asking how galaxies traveled through clusters, astronomers began measuring how stars and gas traveled inside individual galaxies. A spiral galaxy can look almost motionless in a photograph. Its arms appear suspended around a bright center, arranged in a form that seems permanent on a human timescale. But nearly everything in that image is moving. Stars orbit the galactic center. Clouds of hydrogen orbit with them. The entire luminous disk turns, though one revolution can require hundreds of millions of years. We cannot wait for a galaxy to complete an orbit. We do not need to. Motion leaves a signature in light. When material moves toward us, familiar features in its spectrum shift slightly toward shorter wavelengths. When it moves away, those features shift toward longer wavelengths. By comparing these shifts across different parts of a galaxy, astronomers can reconstruct how quickly material is moving at different distances from the center. From that, they build what is called a rotation curve. The idea is straightforward. Measure orbital speed near the center. Measure it farther out. Continue toward the faint outer regions. Then plot those speeds against distance. If most of a galaxy's mass were concentrated where most of its visible light appears, the outer parts should behave in a broadly familiar way. You already live inside a system where something like this happens. The planets of the solar system do not all move around the Sun at the same speed. Mercury, close to the Sun, travels through its orbit much faster than Neptune. Farther from the dominant central mass, orbital speeds decrease. A galaxy is not simply a larger solar system. Its mass is spread throughout a disk, a central bulge, gas, dust, and stars, so the calculation is more complicated. But once most of the visible mass lies inside a star's orbit, astronomers still expect orbital speed to decline with increasing distance if there is little additional mass farther out. That decline was difficult to find. During the 1970s, Vera Rubin and Kent Ford made increasingly precise measurements of spiral galaxies. Their observations showed that stars and gas far from galactic centers often continued moving at unexpectedly high speeds. The rotation curves remained broadly flat instead of falling in the way a distribution based only on visible matter would predict. The result appeared across galaxy after galaxy. This changed the character of the problem. A strange mass estimate in one galaxy cluster could perhaps be blamed on incomplete knowledge of that particular cluster. Flat rotation curves across many individual galaxies were harder to dismiss. There was a pattern. Imagine moving outward through a spiral galaxy, beginning in the bright inner region. Around you are dense concentrations of stars. Farther out, the stellar disk becomes thinner. The visible glow weakens. Eventually, much of the galaxy's obvious light has been left behind, and yet an orbiting star out there can still move, as though a great deal of mass remains inside its path. the light fades faster than the gravitational influence does. To explain this within ordinary gravity, astronomers can place additional unseen mass around the galaxy, not only in the bright disk, around it, extending well beyond most of the visible stars. This surrounding distribution is usually described as a dark matter halo. The word halo may suggest a thin ring, but the physical picture is different. In standard models, the dark matter component forms a large, roughly extended three-dimensional structure surrounding and permeating the luminous galaxy. The bright spiral you recognize from astronomical images occupies only the inner portion of that much larger gravitational system. Measurements of our own Milky Way point toward the same general problem. Modern stellar surveys can trace the motions of enormous numbers of stars, allowing astronomers to estimate the galaxy's rotation curve and the mass distribution needed to produce it. Analyses using data from ESA's Gaia mission continue to find that models including a substantial unseen mass component are required to describe the galaxy on large scales. That means the idea of dark matter is not confined to distant places. If the standard interpretation is correct, the solar system is moving through the Milky Way's dark matter halo right now. There is no sensation of doing so. No wind, no shadow, no visible boundary marking where the halo begins. The sun continues around the galactic center. Earth continues around the sun. Atoms in the room remain atoms. Whatever dark matter is, it does not behave like the ordinary gas that could press against a surface or gather visibly on the floor. Its presence is inferred because the larger gravitational bookkeeping does not work without something like it. This distinction matters. Astronomers did not begin with a preference for invisible material and then search for places to put it. They began with motion. The galaxies moved. The numbers were measured. The visible mass was counted as carefully as possible. And there remained a difference between the gravitational pull that luminous matter seemed capable of producing and the gravitational pull the motions appeared to require. Over time, that difference became harder to treat as an isolated mistake. But rotation curves alone cannot tell us everything. A galaxy is a complicated place. Stars, gas, dust, stellar remnants, central black holes, and uncertainties in how matter is distributed can all affect a mass estimate. Even a repeated pattern invites another question. Can the unseen gravity be detected in a completely different way? There is a way. It does not depend on watching stars orbit. It depends on watching light travel. Because gravity does more than guide the motion of matter. It also changes the path of light itself. And once astronomers learned to use that bending as a measuring tool, invisible mass could begin to leave something remarkably close to a map. Light does not need to touch matter in order to reveal where matter is. It only needs to pass through gravity. According to general relativity, mass changes the geometry of space-time. A beam of light moving through that curved geometry follows a path that can appear bent to an observer when a large concentration of mass lies between Earth and a more distant source of light. The foreground mass can act as a gravitational lens. The lens is not made of glass, it is made of gravity. A galaxy cluster can contain hundreds or thousands of galaxies, along with hot gas and a much larger total mass spread across the cluster. When light from even more distant galaxies travels past such a cluster, its path can be distorted before reaching our telescopes. Sometimes the effect is dramatic. A distant galaxy may appear stretched into a luminous arc. Multiple images of the same background object can appear around the foreground cluster. Under especially precise alignments, the light may form part of a ring. These are examples of strong gravitational lensing, but there is another version that is far more subtle and in some ways more useful. Most Background galaxies are not transformed into obvious arcs. Their images are distorted only slightly. One galaxy may look a little more elongated than it otherwise would. Another may appear tilted by an almost imperceptible amount. For a single object, the effect can be impossible to separate from the galaxy's natural shape. Across thousands or millions of galaxies, however, a pattern begins to emerge. Astronomers call this weak gravitational lensing. By measuring the tiny coordinated distortions in many background galaxies, researchers can estimate how mass is distributed in the foreground. The method does not require that the foreground material glow. It does not require that it contains stars. It only requires enough gravity to change the paths of passing light. This is where the idea of mapping dark matter becomes almost literal. The map does not show dark matter itself. It shows the distribution of gravitational influence. Consider a galaxy cluster viewed through a large telescope. In visible light, the cluster may appear as a collection of bright galaxies scattered across a region of sky. X-ray observations can reveal another major component: enormous clouds of gas heated to temperatures high enough to emit energetic radiation. That hot gas contains a great deal of ordinary matter. In fact, within many galaxy clusters, much of the familiar atomic matter is not locked inside stars at all. It lies between the galaxies as extremely hot plasma, so astronomers can compare different views of the same cluster. Visible observations trace stars. X-rays trace hot gas. Gravitational lensing traces total mass. If the mass inferred from lensing lined up entirely with the stars and gas, then perhaps the older discrepancy could be resolved by ordinary material that was simply difficult to see. That is not generally what the maps show. Gravitational mass distribution can extend beyond the bright galaxies and beyond the densest regions of hot gas. Again, the amount and arrangement of visible matter are not enough to account for the measured gravitational field. One of the most famous examples comes from a system known as the Bullet Cluster. It is not one relaxed cluster of galaxies. It is the aftermath of a collision between two galaxy clusters. On cosmic timescales, clusters can move into one another as gravity draws large structures together. When this happens, their different components do not all respond in the same way. The galaxies themselves are widely separated compared with their individual sizes. During a cluster collision, many galaxies can pass through the encounter with relatively little direct contact. The hot gas behaves differently. Gas particles interact electromagnetically. When the gas from one cluster meets gas from the other, the material collides, compresses, heats, and slows. Much of the ordinary matter in the two systems can therefore lag behind the galaxies during the encounter. This creates a natural separation. The stars in the galaxies continue onward. The hot gas is slowed near the collision region, and gravitational lensing allows astronomers to ask where most of the total mass appears to be. In the Bullet Cluster, the major lensing concentrations are offset from much of the hot X-ray emitting gas. The gravitational mass is found closer to the regions occupied by the galaxies that moved through the collision. This is significant because the hot gas contains most of the cluster's ordinary baryonic matter. If nearly all of the gravitating mass was simply hidden ordinary matter associated with that gas, the lensing map should be concentrated more strongly where the gas collected. Instead, a large part of the gravitational mass appears to have moved through the collision with the galaxies. That behavior fits naturally with a dark matter component that interacts strongly through gravity, but only weakly, if at all, through the electromagnetic forces that cause ordinary gas to collide and slow down. The Bullet Cluster is not a photograph of a dark matter particle. It does not tell us what dark matter is made of, but it places several kinds of evidence into the same physical event. allowing them to be compared in space rather than only in equations. There is visible matter, there is hot ordinary matter, and there is a gravitational pattern that does not simply follow either one. Other colliding clusters have provided related tests, although each system has its own geometry and observational challenges. The larger scientific picture comes not from one famous image, but from the repeated ability of lensing measurements to trace mass that is difficult or impossible to account for using luminous matter alone. This gives dark matter a curious observational character. It cannot be seen directly, yet its distribution can be reconstructed. A telescope records photons from distant galaxies. Those photons have crossed enormous distances before arriving at the detector. Along the way, their paths have been altered by concentrations of mass. The distortion survives the journey. By measuring it, astronomers can work backward. A small change in shape becomes evidence for a gravitational field. A pattern across many shapes becomes a mass map. A mass map compared with visible matter becomes another clue that some of the universe's structure is built from something that does not announce itself through light. There is a human-scale way to think about this. On Earth, we often know an object by the light reaching our eyes from its surface. A chair is visible because light reflects from it. A cloud is visible because droplets scatter light. A person crossing a room can be followed because photons carry information from that person to your eyes. Astronomy usually begins in the same way. Stars reveal themselves with light. Nebulae reveal themselves with light. Planets often reveal themselves by reflected light or by the effect they have on the light of a star. Dark matter forces a different habit. Instead of looking for the thing, astronomers look for what the thing does. The approach resembles watching a shoreline respond to an unseen tide. You may not be able to see the gravitational cause directly, but the motion of everything around it carries information. In gravitational lensing, even the background universe participates in the measurement. Distant galaxies become reference marks. Their light passes through foreground structure and arrives slightly rearranged. The deeper sky becomes a grid through which invisible mass can be inferred. And this is where the scale of the story begins to widen. Dark matter is not only something placed around individual galaxies to explain their rotation, it appears around clusters. It influences collisions between enormous structures. It leaves measurable patterns in the paths of light across distances of millions and billions of light years. If the evidence ended there, the case would already be substantial. But gravity has been shaping the universe for far longer than galaxies and galaxy clusters have existed in their present forms. To understand why dark matter matters so much, we have to move backward in time before all the familiar structures of the night sky had formed. There, the question changes. It is no longer only where the missing mass is. It becomes how the universe grew its structure in the first place. Long before the first galaxies had names, there was already a pattern waiting for them. To reach it, we have to move backward through cosmic history, beyond mature galaxies, beyond the first generations of stars, beyond any structure that a telescope could recognize as a familiar object. The universe becomes younger, hotter, and denser. Eventually, we arrive at a time when there are no stars at all, no planets, no galaxies, no dark lanes of dust between one luminous system and another. Matter exists, but the universe has not yet arranged it into the structures we know. This early cosmos was not perfectly uniform. That small imperfection is one of the most important facts in the story. If matter had been distributed with absolute smoothness everywhere, gravity would have had very little to work with. There would have been no slightly denser regions to pull in more material, no early seeds from which larger structures could grow. Instead, there were tiny differences in density, Some regions contained a little more matter than average. Others contained a little less. The differences were small, but gravity has a useful property when given enough time. A region that begins slightly denser can attract additional material. The extra material makes the region more massive. That increases its gravitational pull, which allows still more matter to gather. A minor imbalance can grow, not rapidly at first, but persistently. This process is called gravitational instability, and it lies near the heart of how cosmologists understand the growth of structure. Dark matter becomes important here because ordinary matter in the early universe was not free to behave in quite the same way. For the first several 100,000 years after the Big Bang, the universe was filled with a hot plasma of charged particles and radiation. Electrons had not yet settled permanently into atoms with atomic nuclei. Photons repeatedly scattered from the free electrons. Radiation and ordinary matter were strongly coupled. A region of ordinary matter trying to collapse under gravity did not move through an empty environment. It was part of a hot, interacting mixture in which radiation pressure resisted compression. Dark matter, in the standard picture, behaved differently. It did not participate strongly in the electromagnetic interactions that kept ordinary matter connected to the radiation field. It could respond to gravity without being pushed around by photons in the same way. That difference gave it time. While ordinary matter remained entangled with radiation, dark matter could begin gathering more freely around the tiny density variations present in the early universe. The gathering was not the sudden construction of finished galaxies. There were no spiral arms appearing in the primordial darkness, no disks, no clusters of stars. The earliest dark matter structures were gravitational concentrations, growing from small initial variations and merging into larger ones. You can think of them not as completed buildings, but as the beginnings of terrain. Shallow gravitational valleys gradually becoming deeper. When the universe had expanded and cooled enough, electrons combined with nuclei to form neutral atoms. Photons could then travel much more freely through space. Those photons are still traveling. Today, we observe them as the cosmic microwave background. It is the oldest light we can study directly with electromagnetic radiation released when the universe was around 380,000 years old. To the eye, if human eyes could somehow detect microwave radiation, this early universe would not present a field of stars. It would appear almost uniform in every direction. Almost. Sensitive instruments reveal tiny temperature variations across the cosmic microwave background. Slightly warmer regions, slightly cooler ones. The differences are extremely small, yet they preserve information about the density variations from which later structure grew. This is one of the reasons cosmologists take dark matter seriously on scales far beyond individual galaxies. A successful cosmological model does not merely need to explain how stars orbit today. It also has to begin with the early conditions measured in the cosmic microwave background and produce, over billions of years, a universe that resembles the one astronomers now observe. Galaxies must form. Clusters must emerge. Enormous empty regions must develop between denser regions. The large-scale distribution of matter must grow from those faint primordial irregularities into the complex structure visible today. Models containing a substantial component of cold dark matter accomplish this remarkably well. The word cold has a particular meaning here. It does not primarily describe temperature in the everyday sense. It means that the dark matter particles, whatever they are, were moving slowly enough compared with the speed of light during the important period of structure formations that small-scale density variations were not rapidly erased. This allows structure to grow from smaller concentrations into larger ones. Dark matter halos form. Halos merge. Matter flows along developing structures. Galaxies later emerge within this evolving gravitational framework. This is sometimes summarized by saying that dark matter provides the scaffolding of the universe. The metaphor is useful as long as it is not taken too literally. There was no completed framework standing empty before ordinary matter arrived. Dark matter and ordinary matter evolved together under gravity, each affecting the total gravitational field. But because dark matter could begin clustering efficiently under conditions that restricted ordinary matter, its distributions helped create gravitational wells into which ordinary gas could later fall. Once neutral atoms had formed and radiation no longer held ordinary matter in the same tight relationship, gas could respond more fully to those gravitational wells. Hydrogen and helium gathered. Denser regions became denser still, gas compressed. Over time, some regions became suitable for the formation of the first stars. Those stars altered their surroundings. They produced heavier elements. They emitted radiation. They eventually died. Later generations of stars formed from enriched material. Galaxies became brighter and more complex, but beneath the visible story was a deeper gravitational one. A galaxy did not simply assemble because luminous matter happened to gather in one place. It grew within a much larger distribution of mass. That helps explain an observation we encountered earlier. When astronomers look at a mature spiral galaxy, the bright disk does not contain all of the mass needed to explain the motion of its outer regions. The galaxy we see is embedded within a more extended dark matter halo. That halo is not an additional feature placed around the galaxy after it formed. In the standard cosmological model, the relationship begins much earlier. The halo is part of the history of the galaxy itself. The Milky Way has this history. Long before there was a sun, long before there was a disk recognizable. As the Milky Way we inhabit today, smaller structures were merging under gravity. Gas was entering gravitational wells. Stars were forming inside developing systems. Those systems combined. Some were absorbed. Others disturbed the growing galaxy and left stellar populations behind. The present Milky Way is the result of billions of years of accumulation, interaction, and reorganization. Its dark matter halo grew through that history as well. This gives us another way to understand why dark matter can feel so difficult to locate. We often imagine an unknown thing as something hidden in a particular place, a planet behind a star, a moon beneath haze, an object too dim for a telescope. Dark matter is not hidden in that way. If the standard model is correct, it is distributed through the same cosmic environment that ordinary matter occupies. It surrounds galaxies. It passes through the regions between stars. It gathers into halos around systems that shine. It extends into larger structures that connect groups and clusters. The hidden part is not its location alone. The hidden part is its nature. Gravity tells us that something is there. Cosmic history tells us that it has been influencing structure for a very long time, but neither tells us what the substance actually is. That distinction becomes more apparent when we widen the view again. A single galaxy is already large enough that light requires tens of thousands of years to cross it. A galaxy cluster contains many such systems, yet even clusters are not the largest organized patterns in the universe. On still greater scales, galaxies are not spread randomly through space. They gather along immense filaments. Clusters form at intersections. Between them lie regions containing comparatively little matter. Together, these structures form what astronomers call the cosmic web. It is one of the largest patterns we know. And in simulations based on the standard cosmological model, much of that web is traced first by dark matter. Imagine the history, not as objects appearing one after another, but as gravity gradually sharpening a faint pattern. At first, the density differences are nearly invisible. Then they grow. Matter drains away from less dense regions. It gathers into sheets and filaments. Filaments feed denser nodes. Galaxies form within those environments. Clusters emerge where matter has accumulated most strongly. The process unfolds over billions of years. There is no single moment when the universe becomes structured. The pattern deepens. A nearly uniform beginning becomes increasingly varied. The cosmic microwave background preserves the early version. The modern distribution of galaxies shows us the later one. Between those two observations lies most of cosmic history. Dark matter helps connect them. This connection is powerful because it asks one theory to succeed across different eras. The same broad model used to describe tiny density variations in the early universe must also account for the growth of galaxies and the distribution of matter billions of years later. It must be consistent with gravitational lensing, with galaxy clustering, with the motions of objects, with the abundance and arrangement of large structures. That does not mean every detail is settled. Cosmology contains active questions about how matter behaves on smaller galactic scales, how galaxies exchange energy with their environments, and whether the simplest dark matter models explain every observation equally well. But the large-scale picture is difficult to reproduce without some component that behaves much like the dark matter in the standard model. For a listener beneath the night sky, the scale of this can be easy to miss. The stars appear separate, a few bright points, perhaps the pale band of the Milky Way. Nothing in ordinary vision reveals that galaxies across immense distances belong to a connected history of gravitational growth. Nothing reveals the invisible filaments between clusters. Nothing shows the early density variations from which those structures developed. Our senses were not built for that scale. Instruments extend them. A microwave detector reads the oldest accessible light. A spectrograph measures the motion of galaxies. A telescope records distant shapes distorted by lensing. Computer models test whether the measured starting conditions can grow into the structures we observe. Each method approaches the problem from another direction, and they keep encountering the same unseen participant. Something contributed, gravity before the first stars formed. Something helped deepen the wells into which ordinary gas fell. Something remains around galaxies today. Something fills the larger web on which galaxies and clusters are arranged. We still have not touched it. We still have not collected a dark matter particle and identified it in a laboratory. The universe has given us a gravitational biography before giving us a name. And that leaves a deeper question waiting beneath the structure. If dark matter has shaped the cosmos for billions of years, what could it actually be? If dark matter is made of particles, then for most of cosmic history, those particles have been passing through places like this one without announcing themselves, through planets, through stars, through the space between them. And, if the standard picture is right, through the region of the Milky Way occupied by the solar system. The difficulty is that gravity tells us almost nothing about the microscopic identity of the thing producing it. A kilogram of iron and a kilogram of water fall in the same gravitational field. Their chemistry is completely different, but gravity does not care about that difference. In much the same way, the motions of galaxies can reveal that unseen mass is present without telling us whether that mass is made of one kind of particle, several kinds, or something that requires a deeper revision of physics. So the search changes the scale. Until now, We have followed dark matter across galaxies, clusters, and the growing cosmic web. Now the question becomes smaller than any telescope image. What would one piece of dark matter be? For many years, one of the best-known possibilities has been a broad family called weakly interacting massive particles, or WIMPs. The name describes the behavior researchers hoped such particles might have. They would carry mass. They would not interact with light in the ordinary way. They might occasionally interact through the weak nuclear force, or through some other interaction of roughly similar strength. That combination once made WIMPs especially attractive, because some theories of particle physics naturally produce stable particles with properties capable of leaving behind roughly the amount of dark matter inferred from cosmology. But a good theoretical possibility is not the same as a detection. To look for WIMPs directly, physicists build detectors in places where ordinary radiation can be reduced as much as possible. One of the most sensitive current experiments is Look Zeppelin, usually called LZ, operating deep underground at the Sanv Underground Research Facility in South Dakota. Its central detector contains several tons of liquid xenon. The idea is to wait for a rare collision in which a passing dark matter particle strikes the nucleus of a xenon atom and produces a tiny, measurable recoil. The experiment is placed underground because the surface of Earth is a busy environment. Cosmic rays arrive from space. Natural radioactivity exists in rocks, construction materials, and the detector itself. Neutrinos pass through the planet. All of these can create signals or backgrounds that must be understood with great care. A dark matter detector, therefore, spends much of its life learning how not to be fooled. In results from several ton-years of exposure, LZ found no convincing WIMP signal and instead placed tighter limits on how strongly certain WIMP candidates can interact with ordinary matter. The experiment continues to collect data. This is an important kind of progress, even though it does not come with the simplicity of a discovery. A null result removes possibilities if a particular type of WIMP interacted too often. The detector should already have seen it. When it does not, the allowed range becomes smaller. Over years, the search space is carved away. WIMPs have not disappeared from dark matter research, but the absence of a confirmed detection has encouraged physicists to explore a much wider landscape. One of the most important alternatives is the axion. An axion would be very different from the traditional picture of a WIMP. Instead of being relatively heavy, axions could be extremely light. Huge numbers of them could occupy the same region of space, behaving in some circumstances more like a coherent field than like an occasional heavy particle crossing a detector. The axion was not originally proposed to explain astronomy. It emerged from an attempt to solve a problem in the theory of the strong nuclear force. Only later did physicists realize that axions with suitable properties could also behave as dark matter. That coincidence made the idea compelling. A particle proposed for one reason might also answer a completely different question about the universe. But here again, compelling does not mean confirmed. Axion experiments use methods unlike the large liquid xenon detectors designed for WIMP searches. Some try to convert axions into detectable photons in powerful magnetic fields. Others search for subtle changes in electromagnetic systems that an axion field might produce. At CERN, axion searches have continued to narrow portions of the possible parameter space, including experiments designed to look for axions associated with the Milky Way's dark matter halo. No axion has yet been established as the dark matter particle. There are other candidates. Some models consider hidden sector particles that interact with ordinary matter through weakly connected mediator particles. Some consider ultralight fields with wavelengths large enough to influence structure on astrophysical scales. Some explore sterile neutrinos, the known neutrinos, hypothetical relatives of the known neutrinos that would not participate in the usual weak interactions in the same way. And some possibilities are not new elementary particles at all. Primordial black holes are one example. The black holes observed through stars and gravitational waves generally form much later, in cosmic history, after massive stars evolve or compact objects merge. Primordial black holes, if they exist, would have formed from unusually dense regions in the very early universe. Because black holes can be dark and massive, it is natural to ask whether a population of primordial black holes could account for some or all of the missing matter. The answer depends strongly on their masses and how abundant they are. Astronomical observations have ruled out large portions of the possible range. Lensing surveys, dynamical effects, radiation constraints, and other measurements limit how many primordial black holes of different masses could be present. Some windows remain scientifically interesting, but there is no evidence that primordial black holes are the dominant dark matter component. The search can also move in a very different direction. Instead of waiting underground for dark matter from the Milky Way to strike a detector, physicists can try to produce something like it in a particle accelerator. At the Large Hadron Collider, protons collide at enormous energies. If a collision produced particles that interacted too weakly to leave signals in the detector, those particles would escape. Physicists would not see them directly. They would look for an imbalance. The particles that are detected carry energy and momentum. If the reconstructed event appears to be missing momentum in a way that cannot be explained by known particles, such as neutrinos, that can provide a clue that something unseen was produced. The logic is familiar now. Do not look for light from the hidden thing. Look for what is missing from the motion. Experiments such as ATLAS and CMS have searched for these patterns in many different kinds of collisions. The searchers have placed strong constraints on models connecting ordinary particles to possible dark matter, but they have not produced a confirmed dark matter discovery. Recent ATLAS and CMS analyses continue to restrict new regions of model space rather than identify a particle. There is also a third strategy. Look upward. If some dark matter particles can annihilate with one another or decay over immense timescales, those processes might produce ordinary particles or radiation. Gamma-ray telescopes can search for unusual emission from regions expected to contain large amounts of dark matter. Other observatories look for excesses of antimatter, neutrinos, or other possible products. This is called indirect detection. It carries its own difficulty. The universe already produces gamma rays, cosmic rays, and neutrinos through many known astrophysical processes. Pulsars, supernova remnants, black holes, stellar winds, and energetic particle collisions can all create backgrounds. A signal that looks unusual must therefore survive a demanding question. Could ordinary astrophysics have made it? That question has erased more than one early excitement, and this is why the dark matter problem can feel so unusual. The gravitational evidence is broad. The particle evidence is absent. We can infer dark matter across scales so large that a single map may contain millions of galaxies, while laboratories searching for its microscopic identity remain unable to say what one unit of it actually is. NASA's current overview lists WIMPs, axions, and primordial black holes among leading possibilities, while emphasizing that no candidate has yet been confirmed. That leaves room for another possibility. Perhaps the missing ingredient is not a new substance in the form we expect. Some physicists have explored whether gravity itself might behave differently from the standard description under the extremely weak accelerations found in the outer parts of galaxies. The best-known family of such ideas begins with modified Newtonian dynamics, or MOND, and extends into more elaborate relativistic theories. These approaches can reproduce some galactic relationships with strike economy. In particular, there are regularities linking the distribution of ordinary matter in galaxies to their observed motions, and modified gravity ideas were developed in part to capture patterns of that kind. But the challenge grows when the evidence expands beyond galaxies. Any alternative has to confront galaxy clusters, gravitational lensing, the cosmic microwave background, the growth of large-scale structure, and systems in which ordinary matter and the dominant gravitational mass appear spatially separated. For that reason, the standard cosmological model still includes dark matter as a real mass component. The unresolved part is what that component is. It may be one particle species, it may be several. It may belong to a hidden sector of physics with its own particles and forces. Or our current list of candidates may be missing the correct idea entirely. There is something almost inverted about this stage of the story. Normally, identifying a substance comes first, and understanding its larger consequences comes later. We learned what hydrogen was, then learned how stars use it. We learned about electrons, then built technologies around their behavior. Dark matter has arrived in the opposite order. We know something about what it has done before we know what it is. It helped shape the growth of structure. It influences the motions of galaxies. It bends passing light. It contributes to the gravitational environment of clusters. And somewhere between those cosmic effects and a laboratory detector lies the missing connection. The next clue may not come from a larger telescope or a deeper underground chamber alone. It may come from comparing dark matter with the visible galaxies that formed inside its gravitational landscape. Because, although dark matter does not shine, galaxies do, and their shapes, positions, motions, and histories may preserve a record of the invisible structures around them. A galaxy carries more than the light we can photograph. It also carries a record of the gravity surrounding it. That record is written in places that can look almost insignificant. A faint dwarf galaxy at the edge of a larger system. A thin stream of stars stretched across a halo. A cluster moving where no bright mass seems to be waiting. Or several distorted images of one distant quasar, arriving by slightly different paths. Each can serve as a tracer, not of dark matter directly, but of the landscape gravity has made. This is useful because a dark matter halo is not expected to be perfectly smooth. In computer simulations based on cold dark matter, large halos grow by absorbing smaller ones. A young universe begins with many small gravitational concentrations. Over time, some merge into larger structures, some are disrupted. Some survive as smaller concentrations orbiting within a larger halo. These surviving pieces are usually called subhalos. A galaxy the size of the Milky Way should therefore inhabit a dark matter halo containing structure within structure. The main halo surrounds the galaxy. Inside it are smaller concentrations. Inside the history of those concentrations are older mergers, encounters and disruptions that occurred over billions of years. Most of that history is invisible. But some of it may leave marks in stars. One of the clearest places to look is among dwarf galaxies. Dwarf galaxies contain far fewer stars than systems like the Milky Way. Some are diffuse and faint enough that their total visible light can be difficult to detect against foreground stars in our own galaxy. Yet the stars inside many dwarf galaxies move as though they are embedded in much more mass than their luminous material provides. In some of the faintest known satellite galaxies, the inferred ratio between total mass and visible starlight can be very large. This makes dwarf galaxies valuable laboratories. There may be only a small population of stars to observe, but those stars move inside a gravitational environment that appears to be dominated by unseen mass. Astronomers measure the velocities of individual stars and ask how much mass would be needed to keep the system bound. The calculation is delicate. A dwarf galaxy may contain only a limited number of bright stars suitable for precise measurements. Binary stars can complicate velocity estimates. Tidal interactions with a larger galaxy can disturb the system. Assumptions about whether the stars have reached a stable gravitational state can affect the inferred mass, so one dwarf galaxy is rarely treated as a simple scale on which dark matter can be weighed. The value comes from populations, different dwarfs, different orbits, different distances, different stellar histories. Together they test what kinds of dark matter halos can host very small galaxies. They also connect observations with simulations. Cold dark matter models tend to produce many subhalos around galaxies like the Milky Way. Not every subhalo is expected to contain a visible galaxy. Some may never have collected enough gas to form many stars. Others may have lost their gas after the early universe was reheated and ionized by the first generations of luminous objects. This means that an invisible subhalo is not necessarily a failed prediction. It may simply be dark in both senses. No stars, no gas bright enough to see, only gravity. How then could such an object be found? One method uses stellar streams. A stellar stream begins with stars that once belonged together. They may have formed in a compact star cluster or inside a small galaxy orbiting a larger one. Over time, the larger galaxy's tidal gravity can pull stars away from the smaller system. The stars do not scatter randomly. They often stretch into long, narrow structures that trace similar orbits through the galactic halo. A stream can wrap across an enormous region of space while remaining only a thin ribbon in the larger gravitational field. That thinness makes it sensitive. If the gravitational landscape were completely smooth, stars in a stream would evolve in one way. If a compact mass passed nearby, its gravity could disturb the stream. Some stars might be pulled slightly ahead. Others might lag behind. A gap could develop. The stream might bend, thicken, or acquire a subtle change in velocity. In principle, an invisible dark matter subhalo could therefore reveal itself not by emitting anything, but by leaving a small scar in a line of stars. This is an active area of research because real streams are not simple laboratory objects. They orbit through the Milky Way's disk, central bulge, stellar halo, and the gravitational influence of visible structures. Giant molecular clouds, the galactic bar, spiral structure, and known satellite galaxies can all perturb stellar motions. A gap in a stream is not automatically evidence for a dark subhalo. The challenge is to reconstruct enough of the visible gravitational environment that an unexplained perturbation becomes meaningful. As surveys improve, the streams become more useful. Precise stellar positions and motions allow astronomers to follow them through six-dimensional phase space, 3 dimensions describing position and 3 describing motion. A narrow band of faint stars can become a gravitational measuring instrument stretched across thousands of light years. There is something fitting in the patience of this method. For generations, astronomers built catalogues by recording where stars appeared on the sky. Positions became more accurate, then proper motions, then distances, then radial velocities. A star that once existed in a catalogue as little more than a point and a coordinate can now become part of a moving structure whose orbit helps reveal the mass of an entire galaxy. The stars have not changed their purpose. Only our measurements have changed what we can ask of them. Dark matter substructure can also be sought far beyond the Milky Way. Strong gravitational lenses provide another route. When a massive foreground galaxy bends the light from a much more distant object, the geometry can produce several images of the same background source. A quasar, for example, may appear in multiple places around the lensing galaxy. If the foreground mass distribution were perfectly smooth, models could predict the relative positions and brightnesses of those images with considerable precision. Small concentrations of mass can disturb the pattern. An unseen subhalo near one light path may slightly alter the magnification of one image. Another may shift by a small amount. In some systems, astronomers can use these anomalies to constrain the abundance and masses of structures too small or too dark to contain visible galaxies. Here again, the hidden object is found through its influence on something else. A stream is disturbed. A lensed image changes brightness. A dwarf galaxy's stars move faster than its visible mass appears to allow. The methods are different, but the logic remains consistent. Follow the gravity. These measurements matter because the smallest matter structures can help distinguish between different ideas about what dark matter is. Cold dark matter allows structure to survive down to very small scales. If dark matter particles were much warmer, in the cosmological sense, moving rapidly in the early universe, some of the smallest density variations could have been smoothed away before they had time to grow. Ultralight dark matter models can alter structure in other ways. Dark matter that interacts with itself through a force beyond gravity could change the internal density profiles of halos. Different microscopic possibilities can therefore produce different astronomical landscapes. The particle may be too elusive for a detector on Earth, yet its properties could still be written across the arrangement of galaxies and streams. This is one reason the dark matter problem joins two branches of science that can seem very far apart. Particle physics asks what the smallest constituents of nature are. Astronomy asks how objects behave across thousands, millions, and billions of light years. Dark matter places the same unknown substance in both questions. A particle property established on a smaller than an atom could help determine how a dwarf galaxy forms. A pattern measured around a distant galaxy could rule out a particle model proposed in a laboratory. The very small and the very large become part of one experiment. There is still uncertainty in this work. The visible matter inside galaxies can reshape their dark matter distributions through repeated episodes of star formation, gas inflow, and energetic outflow. A central concentration of ordinary matter can deepen the gravitational potential. Violent stellar feedback can move gas and alter the motions of surrounding material. Satellite galaxies can be stripped. Disks can disturb subhalos that pass nearby. A simulation that includes only dark matter may therefore produce a cleaner universe than the one nature actually builds. To understand the invisible component, astronomers must also model the visible one well. This makes the problem harder. It also makes it more interesting. Dark matter is not standing apart from cosmic history. Its gravitational structures interact with gas, stars, black holes, and galaxies throughout their evolution. The architecture and the luminous occupants continually affect one another. By now, the invisible framework has been followed in several different ways: through rotation, through lensing, through the early universe, through structure formation, through laboratory searches, through dwarf galaxies and streams. The evidence is not one trail, it is a network, and yet the central object of the search remains absent from our detectors. That absence has begun to change the scientific question. After decades of looking for favored candidates, researchers are no longer asking only which particle fits the original expectation. They are asking how broad the possibilities should be, what assumptions may have narrowed the search too early, and whether the next clue will come from a detector underground, a collider, a telescope, or an observation no one originally designed to find dark matter at all. The invisible landscape is becoming more detailed. Its maker remains unknown. There is another possibility hidden inside the dark matter problem. Perhaps the unseen mass is real, or perhaps gravity itself is telling us that our description of it is incomplete. This idea does not begin by denying the measurements. The stars still move as observed. Galaxies still rotate. Clusters still bend light. The cosmic microwave background still carries the patterns astronomers have measured. The question is what those measurements mean. In the standard model, the answer is that additional non-luminous matter provides the missing gravity. An alternative approach asks whether gravity changes its behavior under conditions we do not encounter very often on Earth. The best-known version of this idea began in the early 1980s when physicist Mordechai Milgram proposed what became known as modified Newtonian dynamics, or MOND. The starting point was simple. In the outer regions of galaxies, the accelerations involved are extremely small, far smaller than the accelerations of falling objects on Earth, far smaller than those experienced by planets close to the Sun. Milgram asked whether Newton's familiar relation between force and acceleration might require modification in this very low acceleration regime. If it did, then stars in the outskirts of galaxies could move more rapidly than expected without requiring large quantities of invisible matter. That is a very different interpretation of the same rotation curve. One explanation adds mass. The other changes the rule connecting mass and motion. This distinction is important because MOND was not created as a general explanation for every cosmological observation. It was first aimed at a more specific regularity in galaxies, and on that scale it has produced results that continue to attract serious attention. The distribution of ordinary matter in a galaxy is closely related to the motion of the stars and gas within it. Where visible matter changes, the rotation curve often changes in a corresponding way. Galaxies with very different sizes and surface brightnesses still tend to follow relationships between their baryonic mass and their characteristic rotation speeds. These patterns are striking because dark matter is not distributed in exactly the same form as the stars, and if a galaxy is embedded in a large unseen halo with its own formation history, then the close connection between ordinary matter and observed acceleration becomes something cosmological models must reproduce. Modified gravity approaches build part of that connection directly into the law of motion. For their supporters, that is one of the strongest reasons not to dismiss the idea. For supporters of particle dark matter, the same patterns are not necessarily evidence that gravity is wrong. Galaxies form through complicated interactions between dark matter, gas, star formation, and energetic feedback. Ordinary matter can cool and move toward the center, stars can explode, gas can be pushed outward. Central black holes can release energy into surrounding material. Over billions of years, visible matter and dark matter influence one another through the gravitational field they share. A close relationship between the two may therefore emerge from galaxy formations rather than from a new law of gravity. This is one of the places where the dark matter problem becomes less like a single mystery and more like a test between competing explanations. A useful theory has to do more than explain one successful observation. It must survive many different environments. Galaxies are one environment. Galaxy clusters are another. The early universe is another. The cosmic web is another. Gravitational lensing adds a different kind of test because it asks not only how matter moves, but how light travels through curved space-time. Any alternative to dark matter must eventually confront all of them. This is where the simplest form of MOND encounters difficulty. Galaxy clusters still appear to require more gravitating mass than their visible material provides. even when modified dynamics are applied. The cosmic microwave background contains a detailed pattern of temperature fluctuations that the standard cosmological model reproduces with a combination of ordinary matter, dark matter, radiation, and dark energy. Large-scale structure also grows in ways that are naturally described when a non-baryonic dark matter component is present early in cosmic history. So, a complete modified gravity theory must extend beyond the original galactic prescription. It must become relativistic. It must describe gravitational lensing correctly. It must work in an expanding universe. It must explain the growth of structure. Several theories have been developed to try to do this. Some introduce additional fields. Some alter the way gravity responds to matter. Some attempt to preserve the successful galactic behavior of MOND while building a broader cosmological framework around it. None has replaced the standard dark matter picture across the full range of observations. But the effort has been scientifically valuable because it forces the evidence to be examined from another direction. Instead of asking only, what particle could produce this gravity? Researchers can also ask, which observations truly require an additional substance, and which might be consequences of an incomplete gravitational law? That distinction matters. Science becomes stronger when a successful explanation is tested against alternatives that make different predictions. A theory is not secure because it is familiar. It becomes secure when different ways of trying to replace it repeatedly fail to explain the same collection of evidence as well. Even then, questions remain. The history of physics contains several moments when an unexplained motion led to very different outcomes. In the 19th century, astronomers noticed that Uranus was not moving exactly as expected. One possible explanation was that Newtonian gravity had failed at great distances. Another was that an unseen planet was perturbing Uranus. The second explanation was correct. Neptune was found. Later, another orbital problem appeared. Mercury's orbit slowly shifted in a way that Newtonian calculations could not fully explain. Astronomers searched for another unseen planet, sometimes called Vulcan, that might be disturbing Mercury. No such planet solved the problem. This time, the missing ingredient was not hidden matter. It was a deeper theory of gravity. General relativity explained the remaining motion. Dark matter sits in a curious historical position between those two examples. The observations could be pointing towards something unseen, or they could be pointing towards something incomplete in the equations. The universe has used both kinds of before. There is no guarantee that it must choose the same kind every time. For someone looking upward from Earth, these debates happen far from ordinary experience. The stars appear to follow familiar paths. Constellations rise and set. Planets move against the background sky. For thousands of years, people used those repeated motions to mark seasons, measure time, and find direction. The reliability of the sky made gravity feel almost synonymous with order long before anyone could write its equations. But reliable motion does not mean complete understanding. A navigator did not need to know general relativity to trust the rising of a star. Newton did not need to know about space-time curvature to describe planetary motion with remarkable accuracy. A theory can work beautifully within one range and still be part of a larger description. That possibility is what keeps modified gravity research alive. At the same time, dark matter has an advantage that becomes stronger when we leave individual galaxies behind. It offers one framework connecting many scales. An unseen gravitating component can help account for galactic rotation, cluster masses, gravitational lensing, the growth of cosmic structure, and patterns in the early universe. That breadth is one reason most cosmologists continue to work within a dark matter framework. The absence of a confirmed particle does not erase the astronomical evidence, but neither does the strength of that evidence tell us which particle exists. So, the uncertainty remains divided into two levels. On the larger level, something in our present description of the universe is producing more gravitational influence than ordinary visible matter can explain. On the deeper level, we do not yet know what physical reality lies behind that influence. It may be a particle that has passed unnoticed through every detector built so far. It may belong to an entire hidden sector of physics. Its interactions may be weaker than researchers first expected. Its mass may lie far outside the ranges that receive the most attention. Or some part of the gravitational story may still require revision. The evidence narrows the possibilities without closing them, and that is where observation becomes most valuable. Different explanations predict different details. The number of small dark structures around galaxies, the inner density profiles of halos, the behavior of colliding clusters, the pattern of gravitational lensing across large areas of sky, the way galaxies assemble through cosmic time, the distribution of matter between the bright regions we can photograph. Each measurement removes a little more room for ambiguity. The next step is therefore not simply to build a detector large enough to catch the unknown. It is also to map the universe with enough precision that the hidden component has fewer places left to disguise its nature across the sky. That mapping is already becoming a new kind of astronomy. Not a search for one dark object, a census of gravity itself. A census of gravity begins with something surprisingly ordinary, a photograph. Thousands of galaxies scattered across a patch of sky may look like a collection of distant islands, each carrying its own stars, dust, and history. But to a researcher studying dark matter, those galaxies can also become measuring marks. Their shapes matter, their distances matter, the small distortions in their light matter. And when enough of them are measured together, the sky begins to reveal not only where luminous objects are, but how matter is distributed between them. This is the scale on which weak gravitational lensing becomes especially powerful. A single distant galaxy has its own natural shape. It may be round, elongated, irregular, tilted, or disturbed by an encounter with another galaxy. Looking at one image, there is usually no way to know exactly how much of that shape was produced by the galaxy itself, and how much came from the gravitational influence of matter along the path its light traveled. But nature gives astronomers enormous numbers of galaxies. Across a large field, their natural orientations are mostly unrelated. The lensing distortions are not. Mass between those galaxies and Earth produces a faint statistical alignment in their apparent shapes. The signal is extremely small, but when many galaxies are combined, the pattern can be extracted. This pattern is often called cosmic shear. It is one of the quietest measurements in modern cosmology. No bright flash announces it. No single image solves the problem. The result comes from averaging tiny changes across large populations until the foreground gravitational structure begins to emerge. With distance information, the method becomes even more useful. A relatively nearby galaxy has traveled through less of the intervening universe before its light reaches us. A more distant galaxy has passed through more structure. By comparing galaxies at different distances, astronomers can build something resembling a three-dimensional picture of how mass is distributed through cosmic time. This is sometimes called lensing tomography. The name is borrowed from techniques that reconstruct internal structure from many partial views. Here, the subject is not a human body or a planet, it is the universe itself. Layer by layer, light from different distances carries information about the matter it encountered. The resulting maps do not identify individual dark matter particles. They do something more suitable to astronomy. They show where gravity has gathered matter on enormous scales. Those maps can be compared with the positions of galaxies. Dense regions of dark matter tend to be places where galaxies are more likely to form and collect. Long filaments connect clusters. Large, underdense regions occupy the spaces between them. The visible cosmic web and the inferred dark matter web are related, but they are not identical. Galaxies are selective tracers. They form only where gas can gather, cool, and build stars inside suitable gravitational environments. Dark matter can occupy regions that contain little or no luminous structure. So the task is not simply to draw a line around the galaxies and call everything inside it dark matter. Astronomers must model the relationship between luminous galaxies and the underlying mass. That relationship changes with galaxy type, environment, and cosmic time. A bright galaxy at the center of a massive cluster does not trace dark matter in exactly the same way as a small satellite galaxy or a faint galaxy in a filament. This is where large surveys become important. The value is not only that they find more objects, they reduce the influence of chance. A small field can contain an unusual cluster or an unusual empty region. A much larger field samples more of the universe's variety. With enough sky, researchers can compare the statistical pattern of galaxies, lensing, and structure against predictions from different cosmological models. The comparison can become remarkably sensitive. Change the amount of dark matter, and structure grows differently. Change the properties of dark matter, and the abundance of small structures may change. Change the way gravity behaves, and the relationship between visible galaxies, lensing, and cosmic growth can shift. The universe becomes an experiment that has been running for billions of years. Astronomers cannot restart it with different settings. They can only measure the outcome carefully enough to ask which set of physical rules is most consistent with what exists. Computer simulations are central to this work. A simulation begins with a model of the early universe. Matter is placed according to statistically defined initial conditions based on observations of the primordial cosmos. Gravity is then allowed to act over simulated time. Dark matter particles in these calculations do not need to represent individual microscopic particles. Each simulated particle can stand for an enormous amount of mass. As the calculation progresses, denser regions draw in more material. Halos form, halos merge, filaments emerge. Large empty regions deepen. The pattern begins to resemble the cosmic web. When ordinary gas is added, the problem becomes much harder. Gas can heat. It can cool. It can form stars. Stars can return energy and matter to their surroundings. Black holes can influence gas across large regions. The visible universe grows out of an interaction between gravity and complex astrophysics. Researchers then create artificial observations of these simulated universes. They can measure the simulated galaxy distribution. They can calculate lensing. They can count halos. They can construct rotation curves. They can compare those synthetic measurements with real surveys. If a model consistently fails to produce what telescopes observe, some part of its physical assumptions may be wrong or incomplete. This is one way the unseen becomes testable. Dark matter is not protected simply because it cannot be photographed. A proposed form of dark matter must produce a universe compatible with observation. Its large-scale structure cannot be arbitrary. Its small-scale behavior cannot be arbitrary. Its influence on lensing cannot be arbitrary. The more precisely the sky is mapped, the narrower those possibilities can become. There is a patient quality to this kind of discovery. Earlier astronomy often depended on recognizing a new point of light. A planet moved against the stars, a comet appeared, A new moon emerged beside a planet through a telescope. Dark matter may not offer such a moment. Its identity could arrive through convergence. An underground detector might find an unusual interaction. A collider might reveal a missing energy pattern. Astronomical surveys might measure a small-scale structure distribution that favors one class of particles over another. Several independent clues could begin pointing toward the same physical explanation. At first, none might be decisive alone. Together, they could become difficult to interpret any other way, or the opposite may happen. Detectors may continue to find nothing. Astronomical maps may become increasingly precise. The simplest particle models may be pushed into smaller and smaller regions of possibility. Modified gravity theories may survive some tests and fail others. The search could remain open for decades. That would not mean nothing had been learned. A mystery becomes scientifically valuable when it forces measurements to improve. Dark matter has already done that. It has encouraged astronomers to measure stellar motions more carefully, map gravitational lensing more precisely, study the early universe in greater detail, simulate galaxy formation at finer resolution, and connect particle physics with the structure of the cosmos. The unknown has become an instrument for discovering everything around it. There is a familiar human pattern in that. For most of history, people learned the sky through what repeated the rising of particular stars, the cycle of the moon, of knowledge came from noticing patterns that remained dependable enough to become meaningful. Modern cosmology uses different instruments, but the habit is related. Measure, compare, return. Notice what persists. A galaxy rotates too quickly. Another does the same. Light bends more strongly than visible matter predicts. The pattern appears again in a cluster, again in a statistical survey, again in the growth of structure. The invisible becomes credible, not because it has been seen, but because independent measurements continue to encounter its effects. And this may be the most useful way to hold the dark matter problem, not as a hidden object waiting behind one final curtain, but as a network of consequences. Gravity has already shown where to look. The remaining task is to understand what kind of reality can leave those consequences across nearly every scale on which the universe has built structure. There may never be a single image that shows us dark matter. No photograph of a particle suspended against a black background. No telescope view in which the invisible suddenly becomes visible. The discovery, when it comes, may look very different from the discoveries we are used to imagining. It may begin as a small excess in a detector buried beneath rock, a repeated pattern in the recoil of atomic nuclei, a faint signal in a carefully shielded electromagnetic cavity, a discrepancy in particle collisions that appears again and again after every known explanation has been removed. Or it may emerge first from astronomy, through a pattern in gravitational lensing, a disturbance in a stellar stream, or the distribution of small structures around galaxies. The answer could arrive from more than one direction at once. That would be fitting. Dark matter entered science through convergence, long before anyone knew what to call it. Galaxies moved in ways that visible mass struggled to explain. Clusters required more gravity. Light bent around concentrations of matter that could not be fully accounted for by stars and hot gas. The early universe evolved into the structured cosmos more naturally when an additional gravitating component was included. Different observations, different instruments, different scales. None of them revealed the substance itself. Together, they revealed its influence. That distinction remains at the center of the story. We know dark matter through relationships. A star responds to a gravitational field. A galaxy responds to the mass around it. A photon changes direction as it passes through curved space-time. A cluster forms at a dense point in the cosmic web. A dwarf galaxy survives inside a halo. A stream of stars remembers a gravitational encounter long after the encounter itself has passed. The unseen becomes measurable because the visible universe does not evolve alone. Everything responds to everything else through gravity. And because gravity reaches across distance, dark matter does not need to shine in order to participate. It has been participating from very early in cosmic history. Before the sun existed, dark matter halos were already growing. Before Earth formed, galaxies were already assembling inside them. Before there were human eyes to study the sky, the Milky Way was already moving through a larger gravitational structure whose full shape we are still trying to determine. Our presence in this story is late. The measurements are recent. The influence is old. That can make the problem feel almost backward. We are not waiting for dark matter to begin doing something. We are trying to understand something that has already been doing its work for billions of years. It helped shape the environments where gas collected. Those environments became galaxies. Inside one of those galaxies, generations of stars formed and died. Their material became new stars, planets, oceans, atmospheres, and eventually observers capable of measuring the gravity that surrounded the entire process. The unknown substance did not need to interact with chemistry in order to become part of that history. Gravity was enough. And perhaps that is why the problem has lasted so long. Gravity tells us where mass must be. It does not easily reveal what that mass is made of. A galaxy can act as a scale without becoming a microscope. A gravitational lens can map total mass without identifying individual particles. A cosmological simulation can show what kind of behavior produces the observed large-scale universe without giving that behavior a laboratory name. Each method carries us closer to the boundary between knowing that something exists and knowing what it is. The boundary has moved. It has not disappeared. Future surveys will map more galaxies and more lensing distortions. Stellar measurements will continue tracing the Milky Way's gravitational field. New observations will test the smallest dark structures that different models predict. Underground experiments will continue listening for interactions rare enough to hide inside enormous quantities of carefully monitored material. Particle accelerators will keep searching for missing momentum and unfamiliar patterns. And theorists will continue asking whether the correct explanation is a particle we have not yet found, a family of hidden particles, an ultralight field, a relic from the early universe, or a deeper change in the way gravity should be described. Some possibilities will fail. That is part of progress. A detector that sees nothing can still eliminate a model. A survey that finds no predicted population can close another route. An observation that agrees with existing theory can make certain alternatives less likely. The search becomes narrower by learning where the answer is not. Eventually, perhaps, one path will remain convincing enough to connect the cosmic and microscopic stories. If that happens, a strange circle will close. The motion of stars in distant galaxies will have helped reveal a new piece of fundamental physics. The bending of ancient light will have contributed to the identification of something smaller than an atom. Structures spanning millions of light years will have told us something about particles too small to see. The largest scales will have explained the smallest. Until then, dark matter remains a useful reminder of how astronomy often works. We do not always begin by seeing the thing itself. Sometimes we begin with an orbit, a distortion, a missing amount, a pattern that refuses to disappear. Then the measurements accumulate. The instruments improve, Alternative explanations are tested. The picture becomes more constrained, even while the central object remains hidden. Tonight, the darkness between the stars looks the same as it did before. A galaxy still appears as light. A cluster still looks like a gathering of galaxies. The Milky Way still crosses the sky without showing the shape of the halo around it. Nothing visible has changed. But the meaning of that visibility has. The glowing universe is not the whole gravitational universe. What shines is only part of what shapes, and somewhere inside, that difference is a piece of physics still waiting to be understood. The stars keep moving through the gravity we cannot see.